So I was still working on this traveling salesman problem again. Thought I was done with it, but then I saw an interesting article, or video, I guess it was both, about, what do they call that, permutations of numbers. The idea being, well, it's hard to describe, but easy to draw out. And I saw that it mapped actually fairly well to the traveling salesman problem. And then by the end of the video, actually, they said somebody used some sort of solver to create better solutions than people had ever seen before. And so I tried it myself to verify, and because I realized my algorithms were different than other people's algorithms. So as long as they have just a distance, I mean, that's all you really need to solve a traveling salesman problem. And so the idea being that I can create a distance metric for something like this. So you can see you have the letters A, B, and B, A. So if you just had, given the letters, two letters, A, B, there's only two different possible ways of arranging them, A and B, and then B and A. If you had three letters, then you would have A, B, C, A, C, B, B, A, C, and B, C, A. I think for all the ones that are unique. The idea being then, given those sequences, what's the shortest sequence you can have of just those letters, containing only those letters? So in the case of A and B, they don't use A and B, that represents all those sequences. It's easier to show it. So if I do A, B, A, for example. So A, B, A has A and B in it, and has B and A in it. But it takes three letters to do the minimum sequence. There's no other sequence for that. The same with A, B, C. If you do them out, there's a sequence that's 9 characters long. Yeah, that's what I have here is the shortest one. Yeah, it's 9 characters long. It's longer to write out, but you can work it out for yourself if you want. Fun exercise. But yeah, that's the minimum that they know of. There's a couple different, I think, of those. But so 9 characters is the minimum that you need. It starts off, well, I can show you why it's that many. I mean, it's like I was saying, it's ABC. So if you're drawing it out, you'd want to have the minimum amount of repeats within your sequence to get the shortest sequence, right? So if you had ABC to start, you just start writing out the sequence. Well, the next letter after ABC would have to be in A. And then because ABC, now we have the sequence BCA. If we put a C there, there's no sequence that has CC in it. And a B, there'd be no 3-letter sequence that had BCB. So, because they're just permutations, they're not combinations. So the permutation is just taking a set of letters and rearranging them some number of times. And they said they're all unique. So if you did that, you'd see like BCA, but then the next one after that would have to be a B, right? So it's ABC, BCA, CAB. And then you keep adding letters until you build up so that you have all those sequences contained within there. And the minimum amount is 9. People had, I guess, been experimenting for years, and they hadn't really realized that you could just apply the traveling salesman problems. And there's an easy way that I came up with to do that. But so going up to the different sequences, there's like for letter 4, it takes 33 letters is the minimum. If you have A, B, C, D, it takes 33 letters to encompass every possible combination in that one sequence. So if someone said, here's the sequence, there's all the letters. And then they got up to 5 was 153. And what was interesting is that they always thought, I guess because they have a way of generating these, they thought, oh, okay, well, this is the best you can do. And they found out, somebody said, oh, no, there's a way of doing 152. And that caused this big controversy, because they're like, oh, no, we have the minimum, we know. But it turned out that there's a bunch of smaller ones. And the same with 6 was 573. Oh, you know, wait, what do I have right there? 873. And they found 872. And then if you look online, people are finding smaller and smaller ones for like 7 sequences and 8 sequences. And so if you have the letters A through G or A through G, H, I, J, each of those, and you just want to arrange them all possible ways, what's the minimum string? And there's just a bunch of people now suddenly applying these techniques. So the thing that I had realized, I mean, their technique is slightly different than mine, but I create like I said, a distance metric for mine. And so the idea being that if you have A, B, C, then the distance between A, B, C to B, C, A would be 1. Because the idea is that you just want to add 1 extra letter to it. So given this sequence here, A, B, C, adding that would only cost 1 extra character. So it goes from length 3 to length 4, and it would encompass both of those sequences. But if the distance between ABC and CAB would be 2, because to get the minimum sequence, you would have to have A, B, C. The first one that would overlap would be the C, so then it would be A, B, C, A, B. And so that's a distance of 1, 2, 3, 4, 5. So it's a distance of 2 extra from this one because the C's overlap. You don't have to do that. And so mostly I count the overlaps and keep that as my distance metric. And then doing that, then I can apply all the stuff I had done from the class for the traveling salesman problem. Some of the things on the traveling salesman problem require on a thing that's called the the triangular inequality theorem. The idea being that if given a triangle like this, or a better triangle than that, if you have this line plus this line, will always be longer than or equal to this line. And by using, a lot of them depend upon that metric. So that works in Euclidean space, right? If you drew a graph, you could always do that. But that's not true with these letter sequences because of the overlap, right? I mean, like in the example, I had A, B, C, and B, C, A, right? So those overlap in 2 places. So the total sequence is only length 4. But if I added another sequence at the end of it and then shifted it back, so then I had another sequence after it that was C, A, B, right? That only adds another one. So that's a total of 5. So it'll be A, B, C, B, C, A. So that comes out that way. So it'll be A, B, C, A. And then the C, A, A, B would overlap that as well. So that would be the sum of those 2 lengths. But then the actual length of this one would be the same as for remove that. What's the distance between this and this? Right? Because these represent a point. This would be this one. This would be this one, or these segments. And this would be that segment there. But this would actually be longer because it's yeah, I drew the wrong sequence, but the idea being that triangle inequality doesn't work out that way. Maybe I'll edit that. No, I don't know. But if you drew the letters, the idea being that the second sequence afterwards, the one that you're replacing it with, if the letters don't overlap, then that becomes longer than the other ones. And I think it shows in that one, but because in the other one it would be I'd add the A to it. I'd have to swap those 2 letters around. It would be B-A-C instead of B-C-A. And then it wouldn't match up. But yeah, so the idea being that doesn't hold true, and a lot of the algorithms depend upon that. As long as you only depend on the distance, then it works fine. So in doing that, I went back and revisited some stuff. So a friend of mine, Frank, was taking the same class, the discrete optimization class, and I told him about some of the algorithms I had for calculating distance and all that, and they depend upon these, like visiting different cities, visiting different nodes within a graph, that generated all possible ones without without repeats, right? So if I had a city tour that goes one way, if I had 5 cities, for example, was the one that he showed me that I had an error with, and 5 cities are easy to draw out. So you just have 5 cities that form like that, say, and you want to iterate through all the possible combinations of those cities so you don't repeat them, but also you don't want to repeat the same direction, right? Because if you want to start here and go all the way around, that's the same distance as going here and going all the way around. And so I looked at the Wikipedia article. There's a couple of them, as well as like Peter Norvig and some other people have sample code of what they do, and they all do it in Python. And I realized because of that, there's an error in how they do their calculations, because they use starting at a point and subtract 1. In Python, that works because you start at 0, -1 just becomes the last point in Python. And C, that's not true in a lot of other languages. And so because of that, I think I can prove that the minimum code that's on Wikipedia is actually incorrect for the operation 2-opt and 3-opt. Because what they do is they actually go too far on some of it. They're actually repeating some of the sequences that you don't really need to. So like on a 5 example here, the way I looked at it was that if you start here, you want to break lines on 2-opt. The idea is you want to swap 2 lines. And in doing so, you're taking all the points in between those 2 and just reversing them. Like if I wanted to go from here to here, and then here to here to here, so you're breaking 2 lines at all times, but you can't break the line next to each other, because if you swap this and this, that you're just swapping that 1 point, and that you can't swap 1 point with itself. But if you have these 2, you can swap these 2, and then have from here to here to here to here to here. And so I looked at it as, well, okay, what you're doing is starting at point 0, you can break that line, and you can break that line. So those are 2 possible things you need to check. You say, oh, is this one, if I take and swap these 2 points, which is the same thing as not doing that tour, but going from here to here and here to here, is that shorter? If it is, then you use it. The idea behind 2-opt is, I want to try something new. I have this path here, but is there a shorter path? And you find the shorter path by swapping points. So those are the only 2 possibilities for that one. So that becomes 2. then you say, okay, well, I'll move to the next side, because we want to try all the possible things to make sure that there's not a shorter path that we miss somewhere. Well, this one here also has 2, because it can break not this one, because that's next to it, if you swap one point, so it becomes that one, and this one's also 2. And the reason that they're both 2 is that this one could touch that one before, and it couldn't touch this one, and the same with this one. This one is unique to both of those. So these get brought in. But then for the last one, this one here can't go to here, because it's already, it's one next to it. It can go to there, so that's 1. It can't go here because it's already been used, and it can't go to that because it's next to it, so that's only a 1. And then this one here, at this point, everything's been gone to. It can't go there, can't go there. It's already gone to there, from there, and there to there. As long as you assume that it's bidirectional, like not in the case of the letter sequences, and actually the direction changes. But in a normal Euclidean space, it's bidirectional, so you can go from the distance between here and here is the same as distance from here to here, whereas in the permutation one, it's not. But I was looking at the original base case here, and I can do a special case for that one. And so it works out to be 2, 2, 1, right? So as I drew out here, and if you do 6, it works out to be 3, 3, 2, 1 for the total possible sides you need to calculate. So what I found is that they actually, and so if you want to work out the equation, I can tell you what the answer is. It works out to be n minus 3 over 2. N times n minus 3 over 2 is the number of actual sides that are unique, that you need to be able to verify to say, oh, okay, is this path shorter or is this path shorter? Whereas if you wanted to compare all the different possible paths, right, you would have to say, well, this one versus this versus this. You would end up being n times n minus 1 times, or n times n minus 1 times n minus 2 over 2, but which is a much larger number. And that's what most people end up doing. But in the Wikipedia article, I saw that they actually, so the code you would do normally would be for I equals 0, I is less than n falls apart, or drops. And in J, you start at equal to 2. So you have your normal loop that's going to loop through all the different possible points. And then J starting at 2, because if you're starting here at 0, then the first one you want to check is this one, because this one doesn't, you're doing that, but you can't do that, anything from that point, so you start here. And for mine, I do forward, so starting at I is 0, in that case, and then I say, okay, well, I want to check the line segment for I equals 0 is I for 0 to I plus 1, whereas they do, starting at 0, they would say I minus 1, they said, because of the Python stuff, but this translates better to C++ as well. But then, so starting at J equals 2, and in order to get this kind of sequence here where the first number repeats, you have to say your range is limited by, it's n minus 3, I said, right? So in the case of 5, the highest number is 2. So n minus 3 is 2. 5 minus 3 is 2. So we want to go up to the most 2, but we also want to repeat that 2. And so we want to do 3 loops. So this loop here would have to go 3 times, right? So 0. So the combinations would be 0, 1, and 2. And so we know then that I can be minus 2 here to be shorter. And on the bottom loop then, we want to be able to repeat that. So in order to do the sequence, the maximum range then becomes, instead of just n, we want to have an n minus I equal to 0. So if I is 0, we want it to be 1 less than it would be. So that way if it's like 5, then it would become, okay, we want it to 4, and we do the same repeat here. And minus the range, for the range ends up being 2. So you end up with a 2, 2, and a 1. And in the case is 5, 5, and a 1. And it ends up being the minimum range. But if you look at the Wikipedia article, they actually do it the other way. They say plus I greater than 1. So actually they're going over by a bit on every time. They're checking the same values over and over again, more than you have to. Whereas if you draw out the sequences, I mean, I'm sketching it out on a piece of paper here, just like I said, mostly want to keep track of my own notes because I spent a lot of time on this, just looking at all the possibilities. And yeah, it works out that the article is wrong, so I was going to try to correct it some way. And then other people I see who are using the code are actually incorrect. There's a TSP lib that I guess has the general source code for the troubling salesman problem with most of the solutions. And I ran that across some of the stuff from the classwork. And it does generate optimal solutions for most of the cases fairly quickly. But it's actually incorrect on its distance. I'm not sure why. I was going to look into the source code. It's kind of a mess of source code, but it returns the wrong distances. It misestimates the numbers, or the final distance that it gives is wrong. It claimed that one of the ranges was 426, but I know the optimal is 428. And when I take their answer that says it's 426, and I tell it to generate that sequence, when I send it into the the class evaluator is my own evaluator. I come with 428. So somehow they're off by 2 in that case. But in other cases, they're the other way. They claim that their number was much higher, but it actually worked out to be lower when you do the calculation. So it's not just a consistent error. So I'm not quite sure how they did that. I'll have to look at the code at some point, maybe. But anyway, I have other projects I'm getting ready to start up. I just wanted to ramp this down and make notes of all the different things I had worked on for it. And yeah, I found that this traveling salesman problem applies to a lot of stuff. So as long as, and I said there's general solvers out there, and you just have to define whether it's a bidirectional thing, like Dick said, the distance from A to B is equal to the distance from B to A. Then it doesn't matter which way you rotate stuff. Or it matters, and then you have to do calculations for the different distances based on a dictionary lookup, is what I did. And so, yeah, it was a lot of fun, and thanks to Frank as well for telling me about the class, and otherwise I would never have heard about it, and I'm glad that he and I were working through it together. Way to go. And I learned a lot of stuff. Yeah, mostly I said I did classwork on my own, but I just missed a couple of loop things, and reading through a lot of the notes and stuff, I just kept thinking, oh, well, here's the equations for how many sides there are, but I hadn't actually sat down and worked out the exact numbers. I thought, oh, okay, just seat of my pants, here it is based on what I saw in the class and reading notes on it, but it seems that they're all kind of wrong, and I'm reasonably sure I'm right. I've verified it and get the same answers, so yeah. Well, anyway, cool. Well, I hope this made some sort of sense, and or at least to me or somebody in the future. And said I'll definitely be using this for other stuff. But cool. Enjoy.